Welcome everyone. My name is Moetazedian. I'm a PhD student at Loughborough University. Today I will be presenting my research on the damage in extrusion additive manufacturing part, the effect of environment and cyclic loading. This research has been undertaken by my supervisory team as well, Andrew Gleadall, Elisa Mele, and Vadim Silberschimdt. Nowadays, the use of biodegradable polymers is increasing rapidly. That's mainly due to their tunable properties, which can be tailored for a specific application. Since they degrade over time, there is no need for secondary surgery, and it eliminates the risk of infection as well as the long-term biocompatibility issue, which is currently associated with the permanent medical devices. Further to these 2 points, biodegradable polymers are 3D printable and relatively cheaper compared to other type of materials. MEAM, which stands for Material Extrusion Additive Manufacturing, is one of the most commonly used technology for fabricating parts out of biodegradable polymers. In this technology, the filament will be fed into the Mele chamber and then it will be deposited onto the print layer by layer. It has been shown that additive manufacturing process saving development costs and time significantly, as well as enabling us to produce patient-specific implants and intricate and complex parts, which is not typically feasible using injection molding technology. However, this layer-wise strategy is normally result in the main limitation of MEAM parts, and that's anisotropy, or more specifically, the weakness between extruded filament as shown by the blue arrows. In contrast, when the filaments are laid down in the direction of tensile testing load, as shown by the green arrow, they're known to be stronger. Therefore, in this study, we decided to consider the weakest part as well by building our tensile testing specimen in the vertical direction. More information about anisotropy and interlayer weakness will be given by my colleague James Allen, so please refer to his presentation. Other than considering the effect of manufacturing process on properties of biodegradable polymers, it's equally important to understand how the environment changes these properties as well. However, we found that many of the studies in literature still consider tensile testing in air at room temperature, whereas in vivo, the medical implant is more likely to be subjected to cyclic loading, as well as it is submerged at physiological temperature, i.e. 37 degrees. So in this study, we propose a correct assessment of medical devices by performing the tensile testing submerging water at physiological temperature. One of the motivations for us to do this experiment was based on our results in the previous studies. So for non-cyclic tensile testing submerged at 37 degrees, we found a considerable reduction and changes in the properties. For instance, we identified that tensile strength and tensile modulus were reduced by 50 and 20% respectively. Meanwhile, the strain at break was approximately increased by 30%. And we identified that the synergistic effect of water and temperature were responsible for the change in the behavior of the polymer. Consequently, the aim of this study was to determine the mechanical properties of the 3D printed part, first by comparing the cyclic and non-cyclic loading condition, and then estimate the damage evolution of 3D printed part once tested in air and submerged respectively. To do so, we decided to print our own tensile testing specimen using the custom G-code developed by us. The benefits of using custom G-code other than using ASTM standards is reducing the thermal variation as well as geometrical complexity, which is normally known to be associated with ASTM standard. The printing parameters are shown in the table on the right hand side, and then schematic showing the toolpath for printing our boxes, which is here as well. Once we printed the boxes, we'll cut them and then characterize them accordingly. So for characterization, we use a macrotensile test equipped with the temperature control biobath, as shown on the figure on the left hand side. And for cyclic loading condition, we use 10% increment of load until failure at a strain rate of 4 times 10 to the power of 4 per second. The other benefit of using our tensile testing specimens is we can actually measure the true load bearing area for our strength calculation as shown by the figure on the right hand side. Let's now move on to the cyclic loading results. In this slide we have the results for cyclic and non-cyclic plot for both air on the left hand side and submerged on the right hand side. We can identify a few differences between these two testing environments. Firstly, the mean ultimate tensile strength reduced by 5 megapascal from 62 to 57 megapascal, as well as we observing some cyclic softening for air specimens. On the other hand, for submerged testing, the reduction was negligible, as well as the cyclic curve followed the master curve, and this may have happened due to the differences between tensile environment. After that, we decided to analyze the stress strain curve more in detail. So we plot the energy dissipation as well as unloading modulus and damage evolution for both air and submerged testing. We identified that during the first 4 cycles, the energy dissipation values were comparable. However, after the 5th cycle, submerged testing resulted in more energy dissipation compared to air. For damage, we identified that the values were comparable initially again, and then submerged testing resulted in sharper increase in the damage value, and at the end it was 18% more damage for submerged testing compared to air. Other than that, we also identified a region of A, which was the overestimation of strain capacity for medical devices. And because of all these differences between these two testing environments, we decided to introduce new safety factor for designing medical implants. So we took the strength at room temperature and then compared against the strength at submerged testing. And then the adjustment was basically multiplying by 2. So we advise future study to use this new safety factor for designing medical implants of biodegradable polymers. After that, we also decided to look at the fracture surface of the tensile tested specimens, both air and submerged. You can see a few differences between them. First of all, there are multiple striations along the fracture plane, unlike air specimens, which showing flat and smooth surface characteristics of brittle fracture. On the other hand, these striations we believe that result in the ductility of the material, as we saw in the stress strain plot as well. And we can see some possible shear lips at the sites. These results are exactly similar to what we've seen for non-cyclic loading conditions. So we believe that these raised edges could be a microplasticity due to the interaction of water molecules with the polymer during its deformation. To summarize our findings, we showed that tensile testing under cyclic and non-cyclic loading resulted in very little difference in terms of ultimate tensile strain and strain at fracture. So this information can be useful for people who design new medical implants. Furthermore, we showed that the correct assessment of polymer for biomedical application is important. Specifically, tensile testing submerged at 37 degrees under cyclic condition resulted in more damage to be accumulated quicker compared to tested in air. So people should consider this for future study. And all of this information was only possible through our novel approach of using our own tensile testing specimens other than using the current ASTM standards. And here I've put 2 of my recent publications. I refer to them during the presentation, so feel free to have a look at them, and also for any more questions, feel free to contact me by my email as shown on the screen. And thank you very much for your attention.